Hello everyone, and today we're going to be doing a derivation that looks into the probability of a binary random variable. We're going to use this in the application of occupancy grid mapping, and it's going to be this thing called log odds, and we'll get to why it's called that later on. Let's take a look at the equation we ended with last week. So we have the probability that a grid cell is occupied, given the probability of my past state history, my past controls, and my past sensor readings. So to make this a little bit less notation heavy, I'm going to simplify this equation a little bit. And what I'm going to do is I'm going to eliminate the controls, and I'm also going to simplify it so we're only predicting the probability of a single grid cell rather than the entire grid. This doesn't change the derivation in a meaningful way, but it does simplify the math so it's a little bit less crazy. The derivation we're going to do is very similar to what we did with the particle filter, because it's using a very similar concept. So what we're going to do is the exact same first step. So we're going to take this probability of z from 1 to t, and we're going to split it off. So this is just a notational shorthand that essentially denotes the same thing as this, so we can do this without really doing anything. So the next thing we're going to do is we're going to use our Bayes rule that we had before. So remember, we have Bayes rule with additional conditionals that takes this form, and what we're going to do is we're going to apply that here. So x is going to equal this, we're going to have y is going to be this z of t, and then the rest of this is going to represent the z in this equation. And we're going to plug these values into the equation and look at what the output is. Remember, Bayes' rule is really convenient because it allows us to write the probability of x given y as the probability of y given x. And oftentimes it's easier to have one than the other. In this case, we want to know what is the probability of a grid cell being occupied, but now what we want to see is what is the probability of a sensor reading given the grid is occupied. So if we use this breakup and apply this equation, we get out the equation below here. So what we've done is we've changed our probability. We still want what is the probability of our grid cell being occupied given the state history and given the sensor reading history. So we can then rewrite that as what is the probability of a sensor reading given that it is occupied, what is the probability it's occupied given our history, and what is the probability of our sensor reading given some history. Now again, remember we talked about this last time, this is very hard to compute. So we're going to keep simplifying this equation to see if we can find a way to actually compute this value. If you remember from our particle filter derivation, we can use the Markov property. And what the Markov property states is that the full history of states doesn't matter. Everything can be encoded in the current state. So we can take this, what is the probability of a sensor reading, given the fact that a grid cell is occupied, with the sensor history and the state history. The probability of getting that sensor reading at the current time using the Markov property only depends on the current state and whether or not the grid cell is occupied. It doesn't depend on the full state history or the sensor readings. This makes a lot of sense. What this is saying is I have some robot, and then what is the probability of me getting the sensor reading I just got, given that the grid cell that I'm looking at is either occupied or not occupied, and my current state. So we can apply the Markov property forward or in reverse, and we're going to use the reverse form in the next equation. So we have what is the probability the grid cell is occupied, given some history of sensor readings and giving some history of states. So we can simplify this out and ignore the last state, x of t. We can do this because we don't have a sensor reading at x of t. The only thing that can tell us whether or not a state is occupied is the combination of a sensor reading and a state at that time. Since we don't have that sensor reading, the state provides no additional information, so we can just drop it off. So we can take these two simplifying assumptions and use it on the equation above. So we can simplify this term using this, and we can simplify this term using this. Plugging those two in below is what we get down here. Now what we can do is we can look at this probability of a sensor reading given the fact the state is occupied and given the current position, and we can then apply the Bayes rule again, because now what we want is what is the probability of m given zt xt. And the reason we do this flip is because when we started off with the flip, it was to simplify an equation that we had, because we could get it out and then use the Markov property. But now what we want is the reverse probability order, because that is more easy to compute. What is the probability a cell is occupied given a sensor reading and a state is better than the reverse? So then we can apply our Bayes rule again. So if we apply our Bayes rule, and remember this would correspond to x in the below equation, this would correspond to y, and this would correspond to z. So the x of t remains conditioned on the entire time. And we can simplify the equation and get the format here. So this is only looking at this under brace section. So we can say what is the probability of z given m and x of t. We can rewrite that using Bayes' rule. Then we can use an independence assumption. Remember when I said that to figure out something about the probability of it being occupied, we require both a state and a sensor reading to determine information. Since this down here is only dependent on the state and not the sensor reading, we can't really say anything about the probability that the grid cell is occupied. So we can drop off the probability, and it's the same because these are independent events. Remember, the probability of something given something else is just equal to the probability of the first thing if they are independent. Knowing more information about y does not tell us anything about x, and this is the exact same idea that we're applying here. Knowing our state at some time t does not tell us anything about whether that grid cell is free or occupied. We need both position and a sensor reading to tell us something about that. So we can rewrite that equation together. So we take off the part that we simplified and write it down here, and this is our new equation. So we're still trying to compute the same probability. So always remember what we're starting with. But now, through application of the Markov property and Bayes' rule twice, we now have this different form of the equation. We've broken it up into different parts. And the idea is that these parts are easier to compute. But now we're kind of stumped. There's not really much else that we can do, and some of these things are really hard to compute. Ideas like this, so what is the probability of z of t given my prior sensor readings and my prior state history? This doesn't really make a lot of sense. What is the probability of some sensor reading given other sensor readings and states? We're not really sure how to compute it. And then also, what is the probability of z of t given x of t? So this is where in the particle filter derivation we kind of stopped and used another trick with normalization to get rid of these terms that are the same. But now we can use the idea that we're computing a binary random variable rather than a continuous random variable like we had in the particle filter case. So I can compute the exact same probability that the grid cell is free or not occupied. So we're going to denote that with this symbol here, which represents not. So what is the probability that it is occupied, and what is the probability that it is not occupied or free? And we get out the exact same equation here. So what do you notice? This term that we talked about earlier that was hard to compute is the same in both equations. And the other term we had issues computing is the same in both equations. So what we're going to do is take this first equation and divide by the second equation. So dividing equation 1 by equation 2 gives us this down here. And then using that, what we're able to do is we're able to eliminate this probability and then this probability. So now what we have is probabilities that are easier to compute and easier to figure out. So we can then rewrite the equation like this below. And using a trick that we talked about earlier, what we can do is write the probability of it being free or not occupied is 1 minus the probability of it being occupied. So then if we look at what we have here, we can break these into discrete parts. This is our sensor update because it is what is the probability of it being occupied given some sensor reading and some current state. And then we have something that represents the history. What is the probability of it being occupied given our history of sensors and our history of states? And then finally, we have this thing here, which is our prior, which is just what's the probability of being occupied in the first place. And you can usually represent this as 0.5 if it's unknown. So you have an equal probability of it being occupied or not occupied, 0 if you're very sure for it to be free most of the time, or 1 if it's likely an obstacle. And then remember, we can then take the log of either side and get something that is represented by sums in the log space rather than by multiplication. This is a really common thing we do when we're computing probabilities practically with a computer because it helps with numerical stability, as well as we can represent things as additions rather than multiplications, which are quicker. So then we can talk about this thing called log odds. So this is a known identity from probability, and we define the odds for a binary random variable is what is the probability of it being true over 1 minus the probability of it being true, which is equal to the probability of it not being true. So then we can go from the odds back to the probability using this equation. So this is really convenient. We have something that represents the probability of something being true over the probability of something being not true. This is the exact form that we had from the prior equation. So now if we look in the log space, you have this new identity. So the log of the same equation, and then you can compute the probability out given it's the log. So we're going to use this for our occupancy grid. And what we're going to do is compute everything in this log odds space. And then whenever we need to use our occupancy grid, we can just export it to a probability using this equation. So we have all the benefits of being in log space. We can do additions rather than multiplications. And also we have this log odds form, so we get to ignore some of the probabilities that are hard to compute. So if we have some grid cell in the log odds space, we can represent the update like this. So this is our sensor update. This is our history. And this is our prior. So we can use this really simple equation to update the probability of a grid cell being occupied. We can just use the current sensor measurement to say whether or not the grid cell is occupied. We can use what are the log odds about it being occupied before, the last step, and then what is the log odds of it being occupied at all. And this equation is parallelizable, which means that I can run each grid cell independently at the same time. So in summary, this is the occupancy grid mapping algorithm. So for each cell, if the grid cell that I'm currently looking at is in the perceptual field of Z of t, which essentially means that I can see it from my sensor, which means I can say it's either occupied or not occupied, and not visible, which we talked about earlier. So then what we can do is update the log odds based on the prior log odds, this thing called the inverse sensor model, which is the probability we talked about earlier, and the prior of the thing being occupied or not occupied. If it's not in the perceptual field, we can't see it, we just leave the probability alone. So in summary, the occupancy grid mapping algorithm is an industry standard because it works. And these are the ideas of why it works. The occupancy grid mapping allows us to compute the probability of each grid cell being occupied. This is really nice. We get a true Bayesian representation of the probability. And the log odd formulation gives us a simple form to update that probability. We can update this very quickly and in parallel. And this thing just works really, really well. That's why it's used in things like the Mars rover or in industry applications. And it's also the idea that's used in the IGVC and roboracing mapping setups. So hopefully you learned something in this video about the idea of probabilistic mapping and how we can use occupancy grids and the occupancy grid mapping algorithm to compute the probability of each grid cell in our occupancy grid being occupied or free. That's all for this week.